Good morning and welcome to Dormer Pramet webinar. My name is Martin Senal and I'm Operation Manager for Dormer Pramet here in North America. I'm really pleased to have you all here for our next second webinar in our program. Today we will take you through some basic insert wear theory, which actually will help you to understand more cutting progress and also help you to get the most out of your tools. So yeah, make yourself comfortable and enjoy the presentation from our product manager, Jesus Nava. And same as the last time, please write your answer whenever you have, write your questions whenever you have, and we will answer all your questions at the end of the webinar. So Jesus, stage is yours.
Thank you, Martin. I appreciate that. As Martin mentioned, welcome first of all to our webinar on turning tool wear and grade selection. I hope after this that it's beneficial in your daily issues that you face on the machines or when looking at inserts to begin with. So, of course, as always, we strive for safety first. That's always our #1 objective for Dormer Pramet. And looking, a grade is chosen based on hardness, chemical, and the application demands. And there is a saying that goes, there is a medicine for each problem, but to choose the right medicine, you need to find the symptoms first. In the case of inserts, this is learned through reading wear mechanisms. Like in the slide above, tool wear tells us that we have chosen the right grade and allows us to look at and adjust our cutting parameters in order to achieve better tool wear results. And as always, we look for predictable tool wear, which allows us to determine at what point in time we should change or rotate the insert that we're using. Tool wear is characterized by two types of phenomena, namely mechanical and chemical. When a mechanical type wear occurs, the insert is damaged by outgoing chips from the workpiece material. This does not change the chemical composition of the surface layers of the cemented carbide. When a chemical wear occurs, the chemical composition on the surface layer of the tool material comes in contact with a chip. This change usually deteriorates the mechanical properties of the surface layers of the tool material and hence their resistance to abrasive wear. As you can see, which area under the wear mechanisms where A and B fall, and then you have the C, D, and E on the right-hand side. And it's indicative as you go towards the right that the cutting temperature increases, allowing for different types of tool wear. And on the left-hand side, the blue area are more of the cooler temperatures, or as stated, the mechanical portions of it. Abrasive wear is a type of mechanical wear. Microscopic hard materials parts come off the tools like abrasive grains during grinding. This type of wear is dependent on the overall path of the tool relative to the workpiece, the shape, size, and the frequency of the abrasive particles and their hardness. Adhesive wear, this is the attrition of the adhesion effect, formation of micro-weldings, between the pure metal surfaces of the cemented carbide and the material to be machined, which come in contact with each other on the flank and top of the insert. As you can see up on the picture up here, the microscopic weld points, the yellow portion is the insert, and the gray portion is the material being cut. Diffusive wear. The atoms of the tool material and workpiece material diffuse with each other to form or create a second solid layer and chemical compound whose characteristics are different from those of the starting material. Oxidative wear. At higher speeds, some parts of cemented carbide react either with air from the surrounding atmosphere or with the cutting fluid replacing the air, or finally with the workpiece material. So the interaction of the chemical components of the insert and the material combined with a heated oxygen air temperature creates the oxidation wear. #1 up here, when you're looking at the purple little circle, at low cutting speeds and feeds, when machining steel, cast iron, and non-ferrous metals, built-up edge will occur, which significantly affects the level of cutting forces and temperatures. And you'll see the #1 in the lower left-hand corner of the picture. Built-up edge is created by particles of machine material which adhere themselves to the cutting edge. It has a significant impact on the quality of the surface finish and the dimensional accuracy of the workpiece and tool wear. And at the lower right-hand corner, you'll see that the yellow portion or slightly blue portion is the insert itself, and what has adhered or the built-up edge is the material that has melted onto the top face of the insert itself. And as this starts to continue to cut, when this built-up edge falls off, it will more than likely absolutely take a piece of that insert with it, and then you'll start to see that in the dimensions and the roughness of the material that you're cutting itself. Built-up edge is not a stable unit. Usually it has two distinct parts, a stable part which adheres firmly to the top of the insert, and a variable part whose height varies during machining. The frequency of change on the variable portion is quite high and can reach 20 to 50 cycles per second. Particles transported by the chip and by the machine material significantly impairs the machine's surface, as well as change the workpiece dimension in the radial direction because the built-up material assumes the function of the cutting edge. And you can see this as an actual picture here. The black portion and the white is the edge of the insert, and the melted portion to the left is the material itself that has already attached itself to the face or the edge of the insert itself, and you can see that in the picture up here as well. So how do we reduce the built-up edge? We can increase the cutting speed, increase the feed. We can also use a coated grade or a PVD coating, or use another more positive or sharp cutting geometry. So number 2, as we climb up the scale here on the left-hand side, so now as the cutting speed and feed rate increase, the built-up edge disappears and the insert will wear by the normal process called flank wear. Flank wear on the tool can be perfectly uniform or may wear close to the nose of the insert and at the end of the depth of cut. As you continue to use the insert, the wear grows down the flank of the insert, as you can see here with a little yellow circle on the side here. When this wear gets to be 20 thousandths or 0.020 inches in length, it is time to index or change the insert. This wear normally would appear after 15 minutes of actual cut time, and universally, 15 minutes is what we expect to see on any cutting edge, and that is accepted throughout the industry. And that is cut time, not movement to or from, its actual cut time. Increased flank wear is caused by outgoing particles from built-up edge. In most cases, flank wear is caused by the contact between the workpiece and the flank of the tool, and will in some cases cause elastic deformation, a buildup of material beneath the surface finish. Very often this phenomenon will occur in fine turning when the selected feed is too low and the tool basically does not cut but instead is forming the chip. So how do we minimize or slow down this effect? You can use a more wear-resistant grade. You can use coolant or increase its intensity, reduce the cutting speed, or if the feed is used under 0.004 inches per rev, then it should be increased. And a rule of thumb for feed when you decrease or increase is normally 10% at a time. Number 3, we further increase the cutting speed and feed rate, and the flank wear doesn't disappear but remains. The dominant limiting factor now becomes the formation of cratering. As the area of contact between the outgoing chip and the face of the insert are run at higher cutting speeds and feed, the wear starts to create a crater. The intensity of the erosion grows as the speeds and feeds are increased. And you can see that is what's formed on top on the left-hand side, the picture here, or on the right-hand side, which is the actual insert itself and the actual formation of a crater. So again, the question arises, how can this effect be minimized or slowed down? We can use a more wear-resistant grade. We can use a coated grade, MTCVD, reduce the cutting speed, or we can use a more positive cutting geometry. Looking at 4 here, if we continue to increase the cutting speed and feed rate, The flank wear will increase as well as the cratering process. But also with the increase, we will create the formation of an oxidation groove on the minor cutting edge. This is a groove at the point where the tool radius has ceased to have contact with the workpiece. And on the left-hand side of the depiction, you'll see it here where the little yellow circle's at, or you'll see it on the top picture on the left, on the right. And that is what we're referring to on the minor edge. So how do we minimize this phenomenon or slow it down? We can use a more wear-resistant grade. We can use a coated grade, MTCVD with aluminum oxide. We can reduce the cutting speed. We can use a more positive cutting geometry, or use coolant, or increase its intensity. So number 5, if we continue to increase the cutting speed and feed rate, then the previous types of wear wouldn't be created because plastic deformation would start to appear. And that's where you see number 5 up here. It's indicative of now starting to get hotter as compared to number 1 where it was a little cooler. Plastic deformation is where the binder has gotten so hot that it is now soft and can no longer hold the grains rigid. It is like getting a piece of plastic hot and pushing on it. It deforms, caused by heat and pressure. So what causes the heat? Friction. The number of feet of material passing the cutting edge every minute, which is called surface feet per minute. And what causes the pressure? Pressure, feed rate. The harder you try to feed the tool, the more tool pressure there is. Therefore, reducing speed, feed, or combination of both will help with plastic deformation. So how do we eliminate plastic deformation or control it? We try to use a more wear-resistant grade. We can reduce the cutting speed or feed, use a positive geometry, or use coolant or increasing its intensity. So until now, we have discussed the adverse effects dependent on cutting condition. And now let's look at other types of wear as well. Flank wear and wear at the top of the insert. This forms when turning gray cast iron and chilled cast iron at lower and medium speeds and feeds. At higher speeds, a crater is created, similar to machining in steel. It is a spot of wear almost identical in appearance on both the face and the flank. As you can see here, the top is the face and the flank is the side of the insert. So we can try to diminish this by using a more wear-resistant grade, use a coated grade MTCVD. We can reduce the cutting speed or use a more positive cutting geometry. Notch wear, formed as a result of machining a hardened layer surface. The higher the hardness equates to the higher the temperature. It's a groove at the point where the depth of cut ends, can be either on the top or on the flank of the insert, as you see it here, the left-hand side with a little circle, or upper right-hand picture, you'll see the notch wear. To diminish the effects, we can use a coated grade, again, use a tool with a smaller approach angle, or we can reduce the feed. Comb rack or thermal cracks. These are cracks perpendicular to the cutting edge caused by abrupt changes in temperature, hot to cold, cold to hot. This happens naturally in milling. You can get the same type of wear in turning if the part is out of round, has an open area, pre-drilled holes, a slot, or even a spline. In turning, we generally go one step towards a tougher grade. It's formed as a result of cyclic recurrence power impact and especially cyclic heat stress. They're actually cracks formed perpendicular to the cutting edge, and they're very regular. On the left-hand side, the animated picture, you see those cracks that are running perpendicular to the lines, and you'll also see them up here on the right-hand side in the middle picture. They're more definite, or on the bottom picture. So to diminish the effects, we can use no coolant and replace that with air to help remove the chips, or we can use a more heat-resistant grade. Chipping of the cutting edge. It happens when you have too high of a power load on the cutting edge, mostly created by vibration or hard chips forming. You have micro and macro damage of the cutting edge. You can use a tougher grade. We can use a less intensive machining conditions to try to reduce that vibration. We can use a cutting geometry which has a stronger edge, or reduce the cutting approach feed, the cut in. And one way of detecting chipping is to run your fingernail or thumbnail along the cutting edge, and you will be able to feel the little chipping effects that are on that edge. Damage of the cutting edge not in cut, or failure of the cutting edge. Mostly from chips, inadequate chip forming causes cutting edge chipping. Micro and macro damage of the cutting edge as well. And you can see that on the back side here of the insert on the left where the circle is, or these two areas on the insert itself. We can try to diminish the effects by changing the feed. We can use another tool which has a different approach angle, or we can use another cutting geometry, or use a more sturdy type of grade. Fatigue cracks. These are cracks along the flank. Formed by cyclic dynamic stress, it creates cracks and then gradually spreads. The fractured surface has a shape or form of shells, as you can see here on the bottom picture. They almost look like seashells that you would find on the beach. To help diminish the effects, we can use a tougher grade, change the way we enter and leave the workpiece. We can change engagement patterns, use alternative coolant, not too intensive. We can change the feed as well, or we can select other geometry. And with Dormer Pramet, we offer a T and an S. The T is for edges with a facet, and the S is rounded edges with a facet. Cutting edge destruction, caused normally by exceeding the power limit or limit conditions of the tool. Brittle fracture of the tool tip. This will more than likely occur in only 3 cases: when you're entering the cut, when you're exiting the cut, or when you cross some inequality or inclusion in the machine material. To help diminish the effects, we can use a more sturdy type of grade, use less intensive machining conditions, use another cutting geometry. We can use an insert with a larger lip or tip radius or nose angle. We can try to stabilize the cutting edge, decrease to a lower feed when approaching the cut as well. But we also can see, feel, or hear this sometimes, what's called symptoms of the tool wear. Visible signs on the insert by looking at the wear on the insert, but there are other indicators of tool wear as well. On the load meter, inserts wear quickly at beginning, then wear slows down, but at some point the wear will increase or be occurring more rapidly. At this point, the insert is not going to last much longer. You can observe this on the load meter. The load will increase rapidly, level out, but continue to grow. Then at some point, it will start to increase rapidly. As the insert wears, it takes more horsepower. We could look at the part size, and that's why we have offsets to help adjust the part size as it changes. The workpiece surface finish. Poor surface finish causes us to change insert before we have 20 thousandths wear, as in a roughing insert. We can also see a burr generation. As the insert wears, it will become dull, causing bigger burrs. The workpiece temperature of the material itself. If you have a short cycle time, the temperature of the parts will increase because of the increased heat being generated by a dull insert edge. Audible vibrations. You know what that sounds like when an insert is cut in correctly, and you should also know what it sounds like when it's not. Visible vibrations. This can be seen on the workpiece surface itself, referred to as the RMS or the surface finish. The chip color. The chip will get darker in color because of increased heat being generated by dull inserts. Of course, that's not for all materials, such as aluminum. You won't get much of a change. Chip control. The chip control loss causes you to lose part of the insert that caused the chip to curl over, work harden, and break. That is assuming that you had chip control to begin with. So up to this point, we've looked at different types of tool wear and some recommendations on how to minimize tool wear effects. Now let's look at the way to help you navigate through carbide turning grades. 3 basic guidelines to keep in mind when choosing an insert. Dedicated inserts are meant to work in certain ISO application-specific workpiece materials. The chip breaker geometry is specifically designed for certain operations. Different geometries are used for finishing operations than you would use for medium machining or roughing operations. Insert grades are specifically designed to perform best in certain materials and under certain machining conditions. Finishing, you get light depths of cut and low feed rates, operations requiring low cutting forces. When you're looking at medium machining, most applications or general purpose, you have medium to light roughing, a wide range of depths of cut and feed rate combinations. And when you look at roughing, it's a high depth of cut and feed rate combinations, operations requiring the highest edge security when you're doing roughing. Grade choices are determined by your machining conditions. You see up here average conditions. They're for the profiling cuts, moderate speeds, forged or cast workpieces. You have good clamping of the component. And to the left here, you'll have continuous cuts, high speeds, excellent component clamping, small overhangs, but more so you'll have an insert that is more wear resistance. And on the right hand side, you have the interrupted cuts, the lower speeds, the heavy castings or forged skins on the workpiece, and possible poor clamping conditions, and you would need a tougher insert. When looking at grades, we need to ask ourselves, what operation am I running and what outcome do I need to have? Because we have a choice of which coating to use, a CVD or PVD. As you can see, a CVD can run very fast. It's a thicker layer, effective against heat, works better with interrupted cuts, and very good crater resistance. But on the other hand, the PVD has a good built-up edge resistance. It's a more universal grade, better in tough applications, and it has a sharper geometry. So when looking at steel grades or ISO-P application area, we can look at the chart above. The CVD coated grade of T9325 would be the first choice for turning of P group materials. It falls to some extent in the mid-range of toughness and wear resistance. In a PVD coated grade, the T8330 is the most versatile of the T8300 series. Being a tougher grade helps in areas of less stable machining. Also, grades listed above to the left of the T9325 or the T8330 shows a more wear-resistant grade, which will help to make the insert last longer in cut, and the grades to the right of the T9325 above are a tougher grade, which helps against adverse conditions, areas, or materials. To make it easier, the lower or the last two digits in a grade are for more wear resistance, and the higher the last two digits, the tougher the grade is. And you can see this, a 5315, the 9310, and the 15, when we're talking about the 10 and the 15, as opposed to the 35 and the 40 on the right-hand side of the 9325. To the left is more wear resistance, as you see on the chart, and to the right is a tougher, indicative of a tougher insert. So when looking at stainless steel grades or ISO-M application area, we can look at the chart above. The CVD coated grade of T7325 would be first choice for turning of M group materials. It gives you higher productivity, allowing for higher cutting speeds, tool life, and operational reliability and suitability for interrupted cuts. When looking at cast iron grades or the ISO-K application area, we can look at the chart above. The CVD coated grade of 5305 would be first choice for turning K group materials such as gray cast irons. If you wanted a harder, more wear resistant grade, that would be. For more of a universal grade for, like, say, both gray and ductile cast irons, then the tougher 5315 would be a better choice, allowing for finishing and roughing and medium to higher cutting speeds. In a PVD coated grade, the T8315 is the most wear resistant of the 8300 series, allowing for higher cutting speeds and improved resistance against notch wear. In the uncoated grade, the HF7 grade is for machining of cast iron. An uncoated grade reduces the coefficient of friction on the insert surface, which helps deter adhesive wear. So when looking at DTM materials, the superalloy grades or the ISO application area, we can look at the chart above. The CVD coated grade of T7325 would be first choice for turning of M group materials such as stainless steels, but as well as first choice for the ISO application areas of S10 through S25 for superalloys, which covers the toughness and wear resistance needed for turning superalloys. In a PVD coating, the T6310 is specifically designed for the S group materials where resistance to high temperatures and thermal cracking is a must. The sharp positive geometry ensures low cutting forces and helps to prevent work hardening. The uncoated grade, HO7, is specifically made for turning of titanium and its alloys. It is a grade with high wear resistance for machining titanium alloys. The chart above is a work in progress. We try to update it as much as we can. It is a good starting point in helping to determine which grade chip breaker to use dependent on material to be machined. It will allow you to navigate through the Pramet Indexable portfolio. You can download this from the handout section in this webinar. Future engagements with your customers. So at this point, we will look
all the time, but we have not received any questions. So I think that we'll wait for a while if any questions will arrive. But if not, you are all very welcome to send the questions to us on our email, cs@dormerpramet.com, and we will come back to you and answer the questions in coming days. As the last time, we will provide you a link to the YouTube video where you will be able to watch and see this webinar as many times as possible and share with your colleagues or the ones who would benefit from seeing this video. So as of right now, there is we received one question. Copy of this slideshow, as said, we will be sending you some materials which were present in the presentation, and also the YouTube video link. So if you need a specific presentation, please come back to us through email. We'll be not sharing that through to all participants. So that's probably the only question we received, Jesus. Do you have anything else?
Not at the moment, Martin. I just wish to thank everyone for attending. And since there are no questions, I wish them have a great day as well.
Thank you. Have a great day.